morning. Welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we completed our discussion on MIMO, that is multiple input, multiple output wireless communication systems, and we summarized the different modules that we covered, different parts that we covered in this MIMO module. Then we moved on to a new module, that is Ofdm, which stands for Orthogonal Frequency Division Multiplexing. Also we said that it's a fairly important new wireless technology, because Ofdm is the basis for 4th generation wireless technologies such as LTE and WiMAX. So Ofdm is a fairly is a thriving and a very key modern wireless technology. Then we also looked at what is the essential idea behind Ofdm. In Ofdm, I look at the available bandwidth B, and I do not use the entire bandwidth for one carrier, but I divide that bandwidth amongst n smaller or n sub carriers. Each sub carrier comprises of a bandwidth of B over n, that is, each sub carrier comprises of a bandwidth. The bandwidth allocated to each sub carrier is B over n. I have n sub carriers, so I am taking a large bandwidth B, dividing it up amongst multiple sub carriers, and I also said I am going to modulate the ith data stream xi onto the ith sub carrier, which is given as e to the power of j 2 pi fit. So I look at xi and I modulate it onto e to the power of j 2 pi fit, that is ith data stream modulated onto the ith sub carrier. And finally, what I do is I put all these different data streams modulated onto the different sub carriers together and transmit the composite signal on the downlink, that is given as yt equals xi e power j 2 pi fit, where I is the ith stream modulated onto the ith sub carrier. Put all these together and transmit the composite signal on the downlink. So that is what we do in conventional, that is what we do in Ofdm, that is transmit the composite signal. And we also looked at demodulation, but I want to go over it again briefly so as to illustrate the point. So we look at, let me just briefly go over the demodulation discussion again for Ofdm. So we said that the composite transmitted signal, in the absence of noise yt, the received signal is nothing but the composite transmitted signal st, which is summation over I xi e power j 2 pi fit, which is also nothing but summation over I xi e power j 2 pi I b over n t, that is the composite transmitted signal, where b over n is the fundamental subcarrier frequency. All other subcarriers are multiples of this b over n, that is I times b over n. Okay. And what I am going to do at the receiver, as we already said, that to decode the nth stream, I am going to coherently demodulate. To decode I am going to coherently demodulate with e power j 2 pi L b over n of t. All right, I am going to coherently demodulate with the subcarrier essentially. All right, so to demodulate the L information stream, and that process is as follows. So I am going to integrate the received signal yt. I am not writing the limits of integration over here yet, that will come slightly later. I am going to motivate what these limits of integration are. I am demodulating with the nth carrier, that is 2 pi L b over n t conjugate dt, and this I am going to write as follows. Remember, I am still not writing anything in the limits. I am going to simply replace this as I x I e power j 2 pi I b over n t times e power j 2 pi L b over n t is a minus because of the conjugate plus dt into dt. And I said this I can split as two integrals. I am still not writing the limits. I can split this as a summation of the term the Lth substream and all other substreams other than the Lth substreams. Corresponding to the Lth substreams, I have e x L e power j 2 pi L b over n t, and I have an e power minus j 2 pi L b over n t. So, both those cancel, and what I have here is x L integral x L, and all other terms corresponding to I naught equals L, I have x I e to the power of j 2 pi I minus L b over n t dt. Now, you can see that b over n is the fundamental frequency. The fundamental frequency of this, if not, if you consider an analog from the Fourier series, is b over n. Hence, the time period of integration for orthogonality is nothing but the time period, this fundamental time period, which is 1 over f naught, which is equal to n over b. Hence, I will write this as, I will write this, in fact, I will write this demodulation now simply as b over n, that is 1 over t times integral 0 to n over b x L plus summation I naught equals n x I e to the power of j 2 pi I minus L b over n t dt. Now, the x L comes out of the integration. This I can write as b over L times x L into n over b plus b over n times summation I naught equals L x I 0 to n over b e to the power of j 2 pi I minus L b over n t. And as we said by the previous argument, this integral 0 to n over b e power j 2 pi I minus L b over n t is in fact equal to 0 for all I not equal to L, because we are integrating over the fundamental period. Hence, this simply this goes to, hence this goes to 0. So, we are integrating over the fundamental period. So, all this goes to 0, and now what we have here is, I am sorry, this has to be a b over n. This is b over n x L into n by b, which is nothing but x L. So, which is the information symbol transmitted on the Lth subcarrier. So, let me write that this is nothing but this is nothing but the information symbol that is transmitted on the Lth subcarrier. So, what I have done at the receiver is out of this composite signal, I am demodulating it coherently with the lth subcarrier so as to recover the information symbol. I can similarly do that for L equals 0, L equals 1, so on up to L equals n, there is n minus 1, that is I can do it for all n minus 1 subcarriers, coherently demodulate with each of those subcarriers to recover all the information symbols. Remember, it is important here to notice that these information symbols are being transmitted in parallel. Hence, let me summarize the ideas. Hence, XL can be recovered by coherently demodulating with e power j 2 pi L b over n t. By coherently demodulating with that appropriate subcarrier, I can recover XL. So, what I need at the receiver are n demodulators e power j 2 pi L b over n t, L equals 0, 1 up to L equals I am sorry, the appropriate index L equals minus n by 2 minus 1 minus n by 2 minus 2, so on so forth up till n over 2, because remember index I is slightly different, it is not from 0 to n minus 1, it is from minus n minus 2 minus 1 to n over 2. Alright. So, by decoding by demodulating with the coherent subcarriers appropriately, I can recover all the modulated information symbols. Okay. So, XL can be recovered by demodulating with this thing. So, I need n demodulators. So, to recover the symbols, to corresponding to n subcarriers coherently demodulate with the corresponding subcarrier for different values of n, with n subcarriers corresponding to L equals minus n by 2 minus 1, so on up to n by 2. Okay. So, by decoding with these different subcarriers, I can coherently demodulate and recover all the n transmitted symbols. So, I am transmitting n symbols in parallel using the composite signals, I am recovering these n symbols which are transmitted on the different subcarriers by coherently demodulating. Now, this is the basis for OFDM. This is not exactly, remember we are still not talking about OFDM, this is the basis for OFDM. So, I want to again clearly mention that this scheme is not, this is not OFDM, that is the scheme that is just illustrated above is not orthogonal frequency division multiplexing. However, it is the basis for orthogonal frequency division multiplexing. It is, however, the basis it is however the basis for orthogonal frequency division multiplexing, that is OFDM, and this is has a name, this scheme that was just illustrated as a name, we are using multiple subcarriers for information stream modulation, this is termed as multi-carrier modulation. The above scheme in short abbreviated by MCM. So, this scheme, the scheme that we illustrated above, is termed as multi-carrier modulation, and it is abbreviated as MCM, which stands for multi-carrier modulation. Okay. Now, also observe that the rectangular detection window is n over b. So, we said the integration time, or in fact the rectangular window for which we have to observe the signal or which we have to integrate is n over b. So, the rectangular window, so the window of time associated the window of time associated with detection of this multi-carrier signal is n over b. So, the window of time, as we said, which is nothing but this is nothing but the time period of integration. Remember, this is nothing but the time period of this also we said is the fundamental period associated with the subcarrier, that is the subcarrier fundamental frequency is b over n, the fundamental period is 1 over the fundamental frequency, that is 1 over b over n, which is nothing but n over b. So, this is the time period of integration, which is also the time period of the observation symbol. So, now we have something interesting. If we look at this MCM scheme, if we look at MCM, I am transmitting n symbols in parallel. Right. It seems like I have this multiple subcarriers, I am transmitting n symbols in parallel. However, I am using n by b time for detection. So, it is not, so what I am saying is it seems like we are increasing the throughput by transmitting these n symbols in parallel, but at the same time our observation time also has increased. So, if we look at this, let me write it out. Hence, this MCM or multi-carrier modulation transmits n symbols using n subcarriers in time n over b, or in time period okay. So, I am transmitting n symbols in time period n over b. So, n symbols in time period n over b implies the symbol rate is nothing but n over b, that is b. So, this is exactly the symbol rate of b, and remember we had seen the symbol rate of b earlier. This is nothing but the single carrier symbol rate. So, if we consider a single carrier system, we are transmitting one symbol in time 1 over b, which means the net symbol rate is 1 over b, which is b. So, the net symbol rate in this multi-carrier modulation system and the single carrier system we had is exactly the same, it is nothing different. So, from symbol rate perspective, we have not gained anything yet using the multi-carrier modulation. So, multi-carrier modulation has exactly the same symbol rate as a single carrier system. So, that is the point I wanted. So, the overall symbol rate from the single carrier to multi-carrier has not changed. So, let me summarize that idea. Thus, the overall in the overall symbol rate in single carrier versus multi-carrier, the overall symbol rate in single carrier versus multi-carrier systems is unchanged, versus multi-carrier is unchanged. Alright, the overall symbol rate in single carrier versus multi-carrier systems is unchanged. In fact, let me just draw this pictorially in terms of picture. In a multi-carrier system, I am transmitting an MCM symbol. So, this is my multi-carrier symbol, multi-carrier modulated symbol. This has a symbol time n over b, and it is transmitting n symbols on, in this I am transmitting n symbols on n, I am transmitting n symbols on n subcarriers. If I consider a single carrier system, then I am transmitting one information symbol at a time, but I am transmitting in 1 by b, time 1 by b. So, in a single carrier system, so this is a MCM, and let me write this as single. In a single carrier system, I am transmitting in 1 over b time, but I am transmitting only one symbol. So, this is one symbol, exactly one symbol. So, one symbol in 1 over b, that is what I am doing in a single carrier system. In an MCM system, I am transmitting n symbols on n subcarriers in time n over b. So, n symbols in n over b, one symbol in 1 over b, they are both exactly same with respect to the system symbol throughput. So, with respect to the system symbol throughput, both of these are exactly the same. So, I want to now draw the schematic of a multi-carrier modulation system that we just described above. So, let me draw the schematic of this. So, schematic diagram. So, let me draw the schematic of an MCM system. I have symbols, so I have the symbol stream that is coming in. What I am going to do is I am going to convert them into parallel. Remember, I have to transmit them in parallel over this n subcarrier. So, I am going to do a serial to parallel conversion, which is nothing but demultiplexing these symbols. I am taking symbols and I am making them into a group of n symbols, because I have to now transmit them in parallel. So, this is a serial to parallel conversion. This is also a demux operation. So, let me write it down. This is also a serial to parallel conversion, because these are transmitted in parallel. So, because we are transmitting n symbols in parallel. Now, what I am going to do is, once I have this parallel, once I have parallelized this, I am going to, as we said, modulate these onto n subcarriers. I am going to take these symbols and modulate them onto n subcarriers. So, this is simply a bank of, remember, each of the n information streams has to be modulated onto its corresponding. This ith stream has to be modulated onto the ith subcarrier. So, I have modulators corresponding to subcarrier F0, F1, so on and so forth, until that is I have to modulate onto this n subcarriers corresponding to I ranging from minus n minus 2 minus 1 to n over 2. So, I have n modulators which modulate these data streams onto the subcarriers. So, let me write it down. This ith data stream is modulated onto the ith data stream is modulated onto the ith carrier. Once I modulate these things, now what I do is I take all these and I sum them, that I form the composite signal. So, I form the composite signal. So, this is a summer. So, which sums them, sums all these signals modulated onto the different subcarriers to form the composite signal. So, that at this summer I sum all the subcarriers. Okay. I sum all the subcarriers to form the composite signal which I transmit on the channel. Alright. So, I send this to the, so once I send this, alright, this is the composite signal. So, what comes out here is the composite signal. So, I have the composite signal which is the output of the summer. The summer simply sums the signals across all the subcarriers, and this composite signal is then transmitted over the channel. Remember, this is just a schematic describing what we had already said. So, this is the transmitter schematic. In fact, this is the schematic of what happens at the transmitter. So, this is transmitter schematic in an MCM system. Remember, we are still at this point talking about an MCM system. So, this is the transmitter schematic of a multi-carrier modulated system. Now, let us look at what happens correspondingly at the receiver. At the receiver, I have the composite signal coming from the channel. This is the composite signal ST. In fact, we called it also YT because we are right now we are assuming, we are neglecting the noise just to illustrate the principles of this multi-carrier modulation. So, this is YT, which is in fact equal to ST in the absence of noise. Now, what I am doing at the composite at the receiver is I have to invert whatever the operations I am doing at the transmitter. So, I have a summer here. I am going to repeat the signal. I am going to repeat it across the n demodulators. Remember, we have the same signal, we have to demodulate it coherently using each sub carrier. So, I am going to here I am going to use a repeater. So, here I am going to use a repeater. I am going to repeat this signal and here I have this bank of demodulators. So, here I have a bank of correlators or demodulators. It is the same thing, we are coherently matching to the subcarrier frequency. So, this is a bank of correlators or demodulators. Alright, this is a bank of correlators or demodulators. This is essentially doing coherent demodulation with the appropriate subcarrier. So, what this carries out is this is coherent with e power j 2 pi f l t conjugate. Remember the Lth subcarrier or the Lth demodulator, I am coherently demodulating the Lth stream, which is e power j 2 pi FLT conjugate multiply and integrate. That is the same thing, that is a correlator, essentially that is the structure we went over. Now, at this output we have the n symbols corresponding to the n stream. So, at this point I have the n symbols. So, at this point I have the n symbols. In fact, these are the n information symbols. These are n information symbols. And now what I am going to do with these is I am going to multiplex them into my serial stream. Remember, I got a serial stream of symbols. I have to again convert it into a serial stream of symbols. So, whatever these n symbols I get, I am going to convert from parallel to serial, or in other words I am multiplexing. So, I am going to convert from parallel to serial, or in other words I am going to multiplex. I am going to mux these and out comes my serial symbol stream. This is nothing but, this block here is nothing but parallel to serial multiplexing. So, what I am doing is I am taking out a serial information. I am starting with my serial stream of information symbols, converting it from serial to parallel, modulating it, summing it, transmitting it across the channel. At the receiver, what I do is simply repeat it, correlate the signal once with each of the different subcarriers, coherently demodulate it. I get the n symbols. Once I get the n symbols, I convert them back from parallel to serial, and which is essentially multiplexing this, and send the symbols to the various applications, or essentially in a 4G wireless system we are talking about several applications that are essentially trying to access the symbol stream. We are going to talk about that a little later, but essentially once these bits are done, we are going to send them to whichever the next processing stage. All right. So, this is the schematic, and in fact this is the receiver schematic in a multi-carrier modulation system. So, let me also write that down. This is the receiver schematic in a multi-carrier modulation system. This is a MCM. This is the receiver schematic of a multi-carrier modulated system, which is fairly simple at this stage, consists of a repeater, bank of correlators, demodulator, and parallel to serial, which sends out the serial bit stream. Now, let us come back, now let us move on. Now, let us see, let us analyze this a little more. So, we have already said, in fact, in the previous slide that we talked about, we already said that this overall data rate is invariant in a multi-carrier modulation system. So, we said overall data rate is invariant in a multi-carrier modulation system. In fact, in a multi-carrier modulation system, I am transmitting in MCM, I am transmitting one, or I am transmitting n symbols in n over b. So, this is n in n over b. We already saw this earlier, and in single carrier or SC systems, single carrier systems, I am transmitting one symbol in 1 over b. So, in multi-carrier modulated systems, I am transmitting n symbols in n over b. In single carrier systems, I am transmitting I am sorry, in multi-carrier I am transmitting n symbols in n over b, in single carrier I am transmitting one symbol in 1 over b. So, the net is I am transmitting one symbol in 1 over b, or the symbol rate is b symbols per second, and this we have already seen, alright. So, single carrier to multi-carrier systems, there is no overall change in the data rate. So, what is the advantage? So, we have said we now have an extremely complicated system which is dividing the bandwidth into different sub carriers, modulating them onto different streams, then again demodulating these different sub carriers, serial to parallel, parallel to. So, we have this huge system, that is this hugely complicated system that we have introduced, but we are saying at the end of it there is really no big advantage, or at least at this point it seems there is really no big advantage over a single carrier system, because the overall data rate at the end of this is the same, it is b symbols per second. So, what is the big idea behind multi-carrier modulation? Let me come back to illustrate that. Let us consider a bandwidth of of 1.024 megahertz, which is essentially equal to 1024 kilohertz. So, now if I use this 1024 kilohertz as it is, this is the bandwidth, this is equal to b. So, now I have two things to do. I have bandwidth of 1024 kilohertz. If I use a single carrier system, I use the complete bandwidth of 1024 kilohertz or 1.024 megahertz, which is much greater than this bandwidth, is much greater than the coherence bandwidth. Remember, several lectures earlier in the initial parts of the course we talked about this important idea, which is the coherence bandwidth, which is approximately 200 to 300 kilohertz. Now, since the bandwidth is much greater than the coherence bandwidth, this becomes a frequency selective channel, and we also said that in time domain it means inter-symbol interference. Hence, a single carrier system in such a scenario experiences inter-symbol interference. Hence, since B is much greater than BC, a single carrier system experiences inter-symbol interference or ISI. Since the bandwidth is much greater than the coherence bandwidth, a single carrier system experiences ISI, which we said is a significant distortion, because the symbols are interfering with each other, which means whatever we receive is highly distorted, and the detection of the symbols reliably is a problem. Now, let us see what happens when we use a multi-carrier system. Let us say I consider an MCM system. So, let me fix the bandwidth at, so B equals 1024 kilohertz. Let me consider N equals 256 subcarriers, alright. So, then what I have is the bandwidth of a subcarrier equals B over N, which is essentially 1024 divided by 256 equals 4 kilohertz. So, look at the bandwidth of each subcarrier in this system. I have 256 subcarriers. I am dividing the net bandwidth amongst these narrow band subcarriers. The bandwidth of each subcarrier is 4 kilohertz, which is much less than the coherence bandwidth. So, this is much less than the coherence bandwidth. This 4 kilohertz, let me write this again, is significantly less than BC, which is approximately 200 to 300 kilohertz. Hence, each subcarrier experiences frequency flat fading. Remember, the bandwidth is much less than the coherence bandwidth, hence the fading is frequency flat and there is no intersymbol interference across the subcarrier. Hence, since B over N is much less than BC, each subcarrier experiences frequency flat fading, all right, because in B over N is much less than BC, each subcarrier experiences frequency flat fading in the frequency domain, which means in the time domain there is no intersymbol interference. Hence, there is no intersymbol interference in time domain. Hence, there is no intersymbol interference in time domain. So, what we have done is we have taken this wideband system, divided into narrowband subcarriers and transmitting narrowband subcarriers in parallel. Now, overall data rate is unchanged. However, implementation wise it gives us a significant advantage because this narrowband subcarriers experience frequency flat fading as their bandwidth is less than the coherence bandwidth. Hence, it is extremely easier to implement reliable detection schemes at the receiver for this narrowband subcarriers because they are ISI free. That is the essential idea behind this multi-carrier modulation, which is to take this wideband channel which is frequency selective and somehow convert it into a channel which is not frequency selective, somehow remove the intersymbol interference. The idea is divide it into multiple narrow bands, transmit the narrow bands in parallel and recover them in parallel, and each subcarrier experience only frequency flat fading. All right. So, that is a very big advantage. In fact, that is the advantage or the motivation behind multi-carrier modulation. Now, let us move on to the next idea. Now, let me go back to the MCM. Now, what is the, so the idea is fine, all right, but what is the problem or what is the bottleneck with this MTM system? So, what is the bottleneck? So, what is the bottleneck in this MCM system? Remember, let me go back to this slide where I showed the schematic of the MCM system. I need a bank of modulators. Conventionally, in a single carrier communication system, I need only one modulator, and implementing that one modulator itself is significantly challenging because I need a modulator implies I need an oscillator and so on, and these oscillators have to be precise, as in the frequency phase has to be precise, and in fact at the receiver also the receiver oscillator has to be matched in phase to the transmitter oscillator, otherwise you will have phase offset and so on. So, implementing this correlators and decorrelators, even one correlator, one modulator, one demodulator is a big challenge. Now, we are saying in this n subcarrier system we have to implement n equals 64 modulators or 256 modulators. So, the number of modulators and demodulators is scaling proportional to the number of subcarriers, which is extremely challenging, and the amount of RF hardware that is required to implement this is not insignificant. It is a fairly challenging task. So, the idea that we are saying here is that the bottleneck is to implement this multi-carrier modulation system is in fact the challenge in implementing this n modulators and n demodulators, which is a significant challenge. So, implementing bank of n modulators and n is so practical. So even though this is a good idea, even though this is a very good idea, seems like a good idea because you are removing intersymbol interference, implementing n modulators and n demodulators is challenging. Alright, okay, so that's a significant challenge, and this was a bottleneck for a long time until there was a key advancements in this area which was made by Weinstein and Ebert. Let me first talk about the people who made this advancement. So there was a key advancement made by Weinstein and Ebert in 1971. So this was by two people, Weinstein and Ebert, which was proposed in their landmark paper, data transmission by frequency division multiplexing using the discrete Fourier transform, using the discrete Fourier transform. That is, there was a technique which we are going to talk about shortly, which solved this problem, which was proposed by Weinstein and Ebert in their paper data transmission by frequency division multiplexing using the discrete Fourier transform. This was proposed in 1971, and both of them, Weinstein and Ebert, were engineers working at Bell Telephone Laboratory. So it was proposed in the 1971 paper, and both of them were engineers. And both Weinstein and Ebert both were engineers at Bell Telephone Laboratory. So they proposed a novel scheme which can be used to overcome this complexity of implementing n modulators and n demodulators, which is as follows. Let me describe that scheme. Consider the MCM transmit signal. Let us consider again the MCM transmit signal. Consider the MCM transmit signal. Remember, we have a bandwidth of B, hence this signal is limited to bandwidth of B, hence MCM signal is band limited to B, hence I do not need to generate the time domain signal, but we have a result from sampling theory in electrical engineering, which we know if a signal is band limited to B, we can sample it. That is, I am talking about the two-sided bandwidth here, not the one-sided bandwidth. So if the signal is band limited to B, hence twice the maximum frequency is B, I can sample at rate B and I can still recover the signal, because B is twice the maximum frequency. I can sample it at B and still recover the signal. Hence, the Nyquist sampling rate sampling rate is B. The sampling time is 1 over sampling rate, which is 1 over B. So, instead of so what I can do is, since this is a bandwidth B limited signal, I can simply sample it at that Nyquist rate B and reconstruct the signal, transmit those samples and reconstruct the signal from the samples at the receiver. Now, let us see what happens when I sample this signal. Remember, the signal or the composite signal ST equals summation I xi e to the power of j 2 pi I b over n t. This is the signal, this is the composite signal. So, this is the in fact, this is the composite multi-carrier modulated signal. Now, what I am going to do is I am going to sample this signal at rate B. Consider the uth sample. The uth sample is nothing but at t equals u over u times sampling time Ts, which is nothing but u over B. Alright. So, the uth sample is nothing but corresponds to time u or B. Hence, the uth sample S of u, or I will also denote this as S of u of Ts, which is equal to small x of u. Let me use this notation. Small x of u is nothing but summation of I x I e power j 2 pi I corresponds to now I and B over n, and t is the sampling time, which is this is u over B. Alright, where now the B's cancel and I simply write this as summation of xi e to the power of j 2 pi I u over n. Hence, the net can be written as x of u I u over n. What we have on the left is the samples of the MWave signal. And now, I do not have to describe what we have on the right, because every student will immediately recognize this as nothing but the discrete Fourier transform of x, the capital X, which is the symbols x0, x1 up to x1. So, this what we have on the right is nothing but the DFT of the information symbol. So, this is the DFT of So, this powerful result by Weinstein and Ebert says nothing but, it says we do not need n modulators and n demodulators. All we need to do is we need to consider the sampled signal, and the samples are nothing but the DFT of the information symbols. Hence, now I have a very efficient way to generate these samples. I do not need modulators and demodulators. All I need to do is take these n information symbols, compute their DFT, that is nothing but the samples of the multi-carrier modulated transmit signal. So, due to lack of time, due to shortage of time, I am going to end this at this point, and we are going to continue this in the next lecture. Thank you very much.